now have about 30 minutes left or so for discussion. I see there have been a whole bunch of questions posed on the Google Doc, and rather than me trying to go through them, I suggest that anyone who has any question that was not answered or addressed in a Google Doc, this is a good point for you to raise your question, or anyone else who wants to take, who wants to start asking any questions, any of the previous speakers, a general question, please go ahead and raise your hand. I said, go ahead, and there we go. Evan, go ahead.
Yeah, I mean, I would love to have a slightly more detailed discussion about this magnetic field question. And I think, partly answered in the chat by Phil was literally what is the physical numerical implementation of magnetic fields. But I was also thinking about in these simulations, how is the magnetic field seated, right? And like, do you have large scale B fields? Because in the simulations you showed, it looked to me like, like you have what could be very large scale magnetic fields, confining the outflows. And I was wondering if you could comment a little bit more on how the magnetic field is treated in general. And then, perhaps Phil could also comment on how this is done in fire.
So we see this in the box directions, I forget which one, say Z, with a uniform magnetic field of 10 to the minus 10 Gauss. And people, not me, have tried to vary this initial seed, and within reason, it doesn't change anything because it's very, very small, and all you need is for the turbulent dynamo to start. Of course, if you've seeded at a much smaller seed, then it will take longer for the turbulent dynamo to like ramp it up to the values we have at redshift 0. But basically, the low redshift stuff is not dependent on this. I don't know. Yeah, I think it's also just a different implementation altogether. So, but it might also not be actually due to the the feedback is also very different. So our ISM model is super smooth, and our winds are launched like basically in the CGM. So we just remove stuff from the ISM and then like reconnect it in the CGM. So there's no actual wind driven in the ISM, and it's just going directly in the inner, like very close to the disk, but still is in the inner CGM. So in that sense, it's also very different because fire has all these explosions that go off in the ISM. And it might also be that rather than the numerical aspect of the magnetic field implementation.
Yeah. And I mean, hopefully Phil can comment, but I guess that was part of my surprise was that, I would say not that you have the same implementation, right? But I would say the fire implementation and the implementation you're using in a repo are more similar, say, than the implementation in Ramses. But like the Ramses global galaxy simulations I've seen with MHD do not have as strong of a magnetic field effect. So I do wonder.
I don't think anyone has studied it so we have also, or I know I haven't. Other people have studied this for the galaxies and concluded that it's an interesting diagnostic, but doesn't change anything about the galaxy properties because it's not it's just not it's not strong enough in the ISM. But then it does make a difference for the CGM. So I think, you can also look at whatever star formation histories and find that nothing changes, and then can claim that nothing changes, but it doesn't mean that the CGM properties won't be different.
Yeah, no, I was specifically referring to CGM properties from some recent sort of galaxy scale Ramses simulations I've seen, but perhaps Phil can comment.
Yeah, I can quickly comment. As was posted in the chat, I mean, the cleaning methods are significantly different, and that is, I think they both use cleaning, but there is a pretty big difference on certain types of problems between the sort of Powell plus deadener and versus Powell alone. So that's definitely a possibility. It's tough to isolate a problem where, as you know, it's tough to isolate a good test problem for this, and I love ideas about that. we have compared informally with the, I think what you're probably referring to with Ramses is like the recent papers by like Martin Alvarez and Sliz and we have compared with their Ramses simulations, which are CT simulations, and roughly speaking, I'd say the amplitude of B in the CGM is closer to what we're seeing in Gizmo or in the fire runs than the repo runs, but I'm hesitant for the reasons Freka said. It is clear that it's sensitive to the feedback models. So so I don't know how much to, that could just be coincidence. I wouldn't overinterpret that result.
Aren't the Martin Alvarez ones really high redshift though?
Yeah, so we took high redshift snapshots and just compared.
But I don't know what the magnetic field strength is at high redshift for us, right? So we have.
Well, Rudiger sent me a couple values, just order of magnitude. We had a series of email exchanges, so it's definitely worth looking more into detail. I mean, this is like, just ballpark numbers. So yeah.
Related to this, what you saw in Frege simulations, where these very coherent magnetic fields sort of seem to drape around that wind, and that could be very different if you have a more stochastic feedback prescription.
Yeah.
And that would potentially be a way in which you could actually discriminate between these different models. Does anyone know whether we have any constraints on coherence lengths of the magnetic field in the outskirts of the Milky Way? I know we have some measures in the ISM, but what about CGM?
I mean, they're barely seeing magnetic fields in the CGM, right? So there's a few measurements now, one with stacking and one with this, I think it was a FRB. But those, you have to assume that the orientation is along the line of sight, and then you get an upper limit, and those are not very constraining yet. But maybe, if we would have like many more FRBs, and they could start to constrain it, especially if it's in the inner CGM where the magnetic field strength will be highest. But you'd need like a much bigger statistical sample.
Yeah, I feel like a lot of this, my impression of a lot of the B field literature is when they say the word halo, they mean like 1 kpc off the disk or something, right? Very different than we're using it.
Okay, Christoph, you have your hand up.
Yeah, I think there are some further rotation measurements, and Rüdiger has written recently a paper actually that Frick is also author on, and he actually found that the magnetic field in the CGM is seeded by the winds, and then there's a dynamo, turbulent dynamo, that actually grows the field quite homogeneously. So I mean, it's this very anisotropic metallicity structure is not mirrored in the magnetic field. In the magnetic field, much more isotropic because of turbulent dynamo that grows there. Now, to sort of respond to Phil, what we have found with these very idealized simulations, and when we vary different models of cosmic ray feedback, so no cosmic rays, advective cosmic rays, and various versions of diffusion, we found that the more you drive winds, the more you quench the dynamo, and the lower the magnetic field that remains there. And it's a potential that if you have a very explosive feedback, you don't allow the dynamo modes to grow the field as it would be otherwise. Potentially that also halts some of the growth. I mean, it's a tricky problem. I mean, I have an answer to this, but it's numerical, it's a physical problem, and the feedback plays in there as well.
Pratik,
yeah, so I think feedback will be very, very important in this, because like if you talk to the dynamo people, right, they talk about this alpha quenching. If you don't have these global outflows which sort of get rid of helicity, then the dynamo process is quenched. So if you don't have like feedback which sort of blows out bubbles as extensively, you can quench the large scale dynamo. So it can be things like that, which is very, very physical. But the feedback implementations can differ. You can have a lot of central heating, whereas these bubbles blowing sort of more distributed. So that can give a big. I think from this logic, that can have a big impact, perhaps bigger than the numerical differences, but I'm not sure. How different are the feedback implementations? I mean, you know, you guys have they are quite different from what I understand, right?
Yes. Yeah.
Yeah, I mean, I think one consequence that's much more, I think, even more obviously related, just going to if you don't mind me interjecting just on this point, related to what you all were just saying. I mean, I think some of the differences we're referring to are manifest indeed in the coherence. So it is very clear that in the fire runs, there isn't the level of coherence that Freyka was showing in the CGM. It's much more tangled and messy, basically. So I agree. These are, thinking about ways to diagnose that more rigorously, even just comparing models more quantitatively in field structure and the extent to which it's disrupting these modes would be very valuable.
I haven't looked at anything high redshift, but at low redshift we still have these very strong outflows, which which lead to this coherence, right? Whereas fire, as far as I know, in the Milky Way mass halos don't drive like these 100 kiloparsec winds anymore. It's mostly like large outflows at higher redshift, and then it sort of calms down at low redshift. So that also may be why it looks quite different. But again, I mean, I have not compared at high redshift, so I don't know what the difference there would be.
Clark.
Hi. If no one minds, I have a question on the transition to sort of a different topic. So yesterday we saw a lot of really beautiful simulations and investigations of sort of idealized setups. But as Freke really nicely showed today, and what I've seen at least in fire, is that the problem of like multiphase gas, at least in the CGM, is very much a cosmological one, and that these different phases are very, very much dependent on density perturbations from cosmological substructure, also feedback clearly. And so I'm wondering, I just want to pick everyone's brains here as to where we should go, in trying to merge these two regimes, because I think it's still pretty disparate. We're still very much trying to figure out like the fundamental physics of multiphase gas, but at the same time, ultimately the setup and the initial conditions are all coming from these cosmological scales. So I was just wondering if anyone had any insight there, because it's a problem that I'm currently grappling with. I don't really know how to interpret all of these.
Anyone want to comment on it? Cameron?
I can comment a little. I know that there are several groups currently trying to merge these disparate scales, building subgrid models. So to try and account for the behavior of cool gas that clearly isn't resolved in cosmological scale, or even possible to be resolved in cosmological scale runs. I know there are several members on this particular Zoom chat who are working on independent models. I think the only one that's been published is by Neil Katz and collaborators, the FEW model that I think was published in the last 6 months or so, that's built into Gadget. But Irina Butsky, who spoke yesterday, and I and Phil and Jess Work and collaborators are working on one. I think Pang and Max and maybe Claude Andre are working on one. But I think I think there's an effort on this front, and I don't think it's great to have to resort to subgrid models, because obviously subgrid models have been a source of lots of uncertainty with respect to feedback for the last 2 decades. But I think that's all we've got, unless cosmic rays are so powerful and dominant that they wash out any small scale structure so we don't have to worry about it. So in my mind, that's the way forward, but other people might have different opinions.
Okay, thank you. Evan.
Yeah, I also can briefly comment. I mean, my first comment is that I think that some of us are trying to work in this sort of intermediate scale regime, right?
Yeah,
and I think
sorry, I should
many of
acknowledge that you're
no, and I didn't mean that as a as a call out. I just meant, I think that is a valid approach, and I am not the only one who's doing that by all means. And I think that trying to connect some of the small scale idealized physics that we saw on day one to some of the larger scales in the way that I and others are doing it is one valid approach. I also wanted to just point out that Drummond and some other members of the SMOG team did something that I thought was interesting, where they compared cosmological type idealized simulations with less idealized but still CGN simulations, right? And I think there were some really interesting implications from that work in terms of maybe some of this idealized stuff is more relevant where the winds in the inner CGM, and you really need the cosmological context in order to understand the multiphase gas in the outer CGM. And so I think that, in addition to the sort of subgrid approach that Cameron was talking about, I think trying to connect these scales, both literally through intermediate scale simulations and through comparing idealized and less idealized simulations in the same context is a reasonable approach that people are trying.
Phil,
I had a question on this note. I guess maybe if I'm optimistic, I would say that what's made subgrid models for small scales so hard in the ISM is that it's fundamentally bidirectional. Your cold phase makes stars that act back outside of your box that you started with in the first place, right? I'm curious, are people worried about some kind of similar effect in the CGM, or in principle, if I gave you all possible boundary conditions for a small scale box and you could just brute force simulate small scale runs of every possible box and give me, their effective chemistry or cooling rate, is that enough? Like, that's not an easy project. I'm not trying to be glib, but that's a more definable project than I think the ISM stuff.
I mean, I think with respect to that, I mean, I may be able to predict with my subgrid model how much cold material is going to form in my cell that I'm not resolving, but I will not be able to track the precipitation of it unless I actually try to model that as well. And I have to have a mass momentum flux through the neighboring shells that is subgrid, and I think that gets very nasty.
Agreed.
I'm not sure whether people have thought about how to handle that. But. Cameron, you still had your hand up?
No, it was just to agree with that statement, that it could be bidirectional. If you are able to precipitate gas that then falls down onto your galaxy and has some sort of cyclical precipitation and star formation, then yes, then it is dependent. But the fact that our current models do a reasonably good job, as Freke was showing, it's not changing. The increase in resolution isn't so much changing the behavior of the galaxy itself, it's just changing the behavior of the resolution of the scales that you're able to see in the CGM. Maybe it's one directional, and maybe my concern is not valid, and Phil is correct here, and all it's going to help us do is match the observations of the CGM. Maybe that would be great, right? A simpler system that's not so nonlinear, but it's hard to know. It's hard to know until we do it.
Peng, you were first.
Just a quick comment about this. So one group of people who've been relatively successful at this is people trying to block white dwarfs as type 1a supernova. So the separation of scales is actually, just as challenging as what we have. They're about 10 to the 7, a factor of 10 to the 7, and you need to resolve a nuclear burning front, which is extremely hard, which is very temperature and density sensitive. And they seem to have reasonable models. So that's maybe a field where we can get inspiration from.
Thank you. Juan.
Yeah, I just wanted to add to that. I've been trying to set up a small patch representing the CGM, and I think it's really hard. That's why I haven't done it. So apart from all this feedback that we discussed, it's also just really hard to set up the initial condition because we know how to drive perfect turbulence, right? Every simulation code comes with that test. But recently, I think Cassie Lockhart had a paper where she looked at the kinematics of the gas in the CGEM, and it's you know, highly time variable, and it's not perfect turbulence. So I don't really know how to put that into a small box. Yeah, it's hard.
I believe you. I wouldn't know how to do it either. Let's see.
Can I ask a question?
You just did.
I can't raise my hand. I was just wondering if people have given any thought to whether this statement that this enhanced resolution in the CGM has no, or at least very minor effect on the galaxy itself. Could that perhaps be a mass and redshift dependent statement that we just have not sufficiently explored? And whether we go to massive galaxies at high redshift, where we expect there to be a lot more dense cold gas inflowing at high velocities, which we may not be treating properly, whether that could feed back more onto the galaxy itself? Is that something people have thought about?
Great question. Thank you. Anyone want to comment?
Well, I don't have any. Oh, sorry, Cameron, go ahead.
No, I mean, it's absolutely possible, Nir. And there's a lot of phase space of galaxy masses and redshifts that we'd have to probe with this. And thus far, the work by the Foggy consortium and Freke's group and my group have been pretty limited in terms of the number of halos that we've been able to do with this. But the fact that existing cosmological galaxy evolution simulations, whether it be Fire, whether it be Auriga, whether it be Illustris, whether it be Eagle, are doing a reasonable job of getting a lot of the bulk properties of galaxies correct, leads us to think that we're doing something right, and it's not super non-linearly dependent on these effects. But as I said, like
well, but I mean,
getting the right answer for the wrong reasons too.
So that's right. I mean, they can't all be getting the right answer for the right reason, because they're doing everything very different.
I mean, one point to make is for all of these mesh codes, like they're solving in co-moving coordinates, right? So their resolution is actually much better. like when Franco was showing that plot of cell radius for like cell size versus radius, like that was for redshift 0, but you know, she's probably like, well, she can say, and Cameron can say, because they've done mesh simulations, like it's, you know, it's a later redshift issue for the mesh codes. So I don't know, but I think the limitations are just statistics. Like each group has done like one halo, and then the full halo mass range.
Foggy now has 6 halos,
okay.
or at least a new version that refines on the cooling rates. But they haven't, like the paper that's out, Foggy 4, just like goes into RAM pressure and doesn't really go into like how it's different with resolution. That's why I didn't really mention it. So I don't know, but they in principle should be. I don't know if any of their team are here, but they in principle should know whether or not there's any like trends or something. I do want to say that even for my highest 500 parsec run, I did see an increase at late time star formation. If I've rerun that without AGN and whatever, just because I'm doing other experiments, and that's always the case. But again, that's so it's a different feedback, but it's still the same halo. So because I'm using the same initial conditions, so it's not a great sample, but I'm starting to feel like that might actually be robust, and then so we might end up with needing a bit more feedback to stop this additional late time star formation to make Milky Ways.
Clark.
I also kind of, admittedly, my one zoom in contribution to this is at redshift 6, so it's kind of very different to what everyone else has done looking at the boosted resolution. But we did start to find kind of an increase in star formation rate, but because it was just kind of a test, we haven't seen if that continues down to low redshift and how it affects feedback and various things. It did seem to change not only the amount of star formation, but the distribution of it as well, because you ended up with cold, dense gas further out in the halo. Admittedly, it's a fairly simplistic model of star formation, etc., but that might also make a difference.
Thank you. Clark, you've been waiting for what?
So I actually have a question on the numerical side about these enhanced resolution CGM simulations. And this is coming from, so whenever I like talk about any of these papers because they're all really cool at my like group meetings with Nick and Andre, they always ask whether or not these simulations also enhance the resolution in the dark matter particles. And my impression from reading the paper is that they don't. And I'm wondering if everyone, because there are several people on this call who have been running these simulations, who are doing so, could maybe comment on the numerical effects that might have or lack thereof.
I think it's correct, Freek, right? That you guys are you're not increasing the dark matter resolution.
No, we're not, and I don't think it matters. But I don't know. Like maybe Cameron has a good physical explanation or numerical explanation.
So yeah, we don't, and I don't believe Foggy does either, increases the dark matter resolution at all with the increase in the hydrodynamics. I think this can be a problem only at extremely fine resolutions in the gas and coarse resolutions in the dark matter, where you might get like body effects from like scattering and such. But at the resolutions that we're able to achieve on the order of a few hundred parsecs, I don't think this is an issue. I have a small section in the Tempest paper that's about this, but I don't remember the details of it off the top of my head.
I mean, one thing I'll point out, I mean, I think like it's still the case that the smallest cells in both these simulations are in the ISM in the disks, right? It's not like you have reduced the minimum cell size of the simulation, right? So I wouldn't predict that it would produce numerical artifacts if it didn't in the fiducial run.
Well, the only difference is that the density of dark matter particles in the CGM is much lower than it is in the core of the galaxy, and so then you could start getting some scaling effects at, even though you have the same hydrodynamic spatial resolution between those two regions. But I think you're still okay at the level that we're doing it, but maybe increasing to the levels that Evan Schneider's able to achieve in her simulations.
I think the only place where it matters is the amount of substructure you're resolving, and then small satellite galaxies, and that would take up some gas that is initially hot might now be cold because it's able to cool inside the smaller potential wells, which you're not resolving in one case. So that would have an impact, but.
Aren't there some studies that also like say that for some very peculiar things that you actually need to have the same gas and dark matter resolution? So we don't have that even in standard simulations, right? There's always a factor of 5 difference because we have the same number of resolution elements, which means that we have more massive dark matter ones. And I think for the vast majority of things that we study in these simulations, it just doesn't it doesn't make it doesn't have a dominant or noticeable effect. But I think there was some paper from maybe the Eagle group that like tried this and found like some case where you actually needed to have the same resolution.
In the Romulus simulations, I believe they oversample dark matter particles to get equalness.
Do you know why?
No, but I know that they do.
Yeah, Frick is right. There was a paper by the Eagle folks that showed that if you actually had the same mass dark matter particles as their hydro particles, that it changed the structure of the disk perceptibly. Although I don't recall the effect. But it's also worth mentioning, right, that this is all really different from particle codes to grid codes, right? Grid codes are coupling to the gas in a whole different way anyway. So
I think if you're an SPH, then you want to be worried about segregation effects and stuff like that. I think Max had his hand up first.
Thanks, but I mean, if Phil wants to comment on exactly this point with the dark matter, then he should go ahead.
Well, yeah, I just had a very quick comment that I think the arguments people have made about this here, related to what Frank was mentioning, are really relevant in halo centers. You know, at a few softening lengths, which is the disk for the Eagle type simulations, where numerical relaxation and convergence is, you know, sensitive, but it's really where you've got sort of, very halo centers where n-body relaxation and strong self-gravity effects are what's most important. I think it's hard to imagine those effects generalizing to the CGM, but then again, I haven't tested it.
Yeah, so the point I wanted to ask about was connecting to what Cassie wrote in the chat. And so can one disentangle these, like butterfly effect versus resolution effect in these kind of simulations? I was wondering about that.
I mean, people have done, like, was it Shaganel who did like a whole butterfly resolution thing? So I think what's important in this case, if you want to do it, is that you have to have your code so that it actually does reproduce the same thing. If you use exactly the same number of cores, the same initial seed, etc. Right? But then you get the same answer, and then you can like make a tiny perturbation and see what kind of answer you get. And I think it may be that not every code like always has that stability, that it will give the same answer if you don't vary anything. So so that might be that might complicate this. And I don't know about Enzo and Foggy, so I don't know if they struggle with this. I think Arepo, from this study with TNG that Shai did, I think we have a good handle on, that fluctuations like less than 0.1 dex are because of like chaos, just tiny differences.
Correct. You want to comment?
Yeah. I think actually just to reiterate on that point, I think the question is really since you only run sort of addressing Ricky here, but I think this goes for all these high resolution. Since there's only a small number of halos, and this is what Cassie was trying to say, I think, it's hard to know whether more mass is because of a systematic resolution effect, or because there's been some sort of change in the large scale evolution because of small scale differences, which cascade to larger scales. And actually, in that vein, I wanted to ask, because you showed quite nicely that the covering fractions were quite a bit larger for the cold gas. But I was wondering, is there the same sort of difference in the total amount of mass of cold gas? And have you looked at that? Is that ratio sort of stay the same over time, which would argue against a sort of a butterfly effect, or is that something that does fluctuate quite a bit?
If you're addressing me, so the overall mass is completely dominated by the thick H1 disk around the galaxy, and so that doesn't change because the resolution doesn't change there. I think if you integrate, like, let's say only from 50 kpc outwards, then and cut out the satellites, then you will get an increase in cool mass there. But I don't know how it changes with time, and it's partially because the way I've done it is keep the physical resolution the same. So basically, my high redshift simulations are identical to a normal mass refined simulation, and I only start seeing differences below redshift 1 or so. So perhaps people who made co-moving choices know more about time evolution.
I can speak to that a little bit. It's consistently higher cool gas mass. I have a table in the paper that shows this for higher resolution. But again, as Greg points out, and as was raised by Cassie, it's a single halo, so it's hard to make broad statements about this sort of thing from a single halo.
If we have time, could I ask one more question of Freke?
We already did.
No, that was to you. Freke, something you didn't mention, but I do know that you have thought about it a lot, and I don't remember what you found. Are you, in terms of measuring H1, are you at all concerned that a way self-shielding is implemented in these simulations is no longer valid, given the kind of small scale clouds that we're now resolving in the outer CGM?
I mean, worried. I mean, I know that I don't trust it, but I also don't trust no shielding. So I redid all the simulations without any shielding, which I think should bracket the possibilities, right? Like having too much and having too little. And of course, it changes the normalization of like, if you think about this H1 profile, but the difference between with and without this enhanced resolution is very similar. We still get well, maybe slightly smaller effect, but still like an order of magnitude effect in if we have them without any self-shielding. But of course, if you wanted to like, if you wanted to build your statistical sample to actually, and like, well, first you would, to actually compare to observations, you would have to be converged, you would have to have good radiative transfer to do your self-shielding properly, and you would have to have your statistical sample of halos, including too much lower masses, because that's what most of the observations actually probe. So I think we're quite far away from that. So I was mostly looking at differential effects, and I think those are independent of how terrible we do our self-shielding.
Good answer. Thanks.
Okay, since we are 20 minutes over the official allotted time, I think we should slowly start to wrap it up. If there's anyone else who wants to make an infamous final remark, this is your chance. If not, then let me take this opportunity to thank Christine, Chad, and Nir, who have been doing all the work here in organizing this. I was just a tag on. So thank you so much. I'm really proud as well. Everyone, thank you for organizing this fantastic meeting. This was great fun.
Thank you to you as well, Frank, for
co-organizing. Really, it was all Chad and Nir. I did very little.
Well, we should say thanks to KITP, because this conference came together as a way to give KITP postdocs a chance to organize a series of conferences. So it's been a fun opportunity.
It's still a lousy excuse.
One of many.
Can I also advertise for a very similar KITP program that will be happening in 2 months? For those of you who don't know, there's a program called Fundamental Properties of Gaseous Halos, I think is the title. I can put the link in the Google Doc, or in the Slack. But it's a 2-month-long program that's on very, very similar topics to what we've covered the last 2 days. And because it's being done primarily all remotely, you'll be able to connect. It's not limiting the number of people who can participate, much like this one did. So there will be essentially from 8 a.m. to 10 p.m. 8 a.m. to 10 p.m. That would be too much. 8 a.m. to 10 a.m. Every weekday for about 7 or 8 weeks. For January and February, you can connect to a Zoom session, and there will be stuff like this, discussions, coffee, presentations, meet and greet sort of stuff. So I encourage you to check it out, and we'll have more details on the website soon.
Great. So hope to see many of you there in 2 months. In the meantime, stay safe. Easier said than done. And all the best. And thank you everyone for contributing to this fantastic meeting. So thank you.
Thank you. Bye-bye.
Yeah, thank you.
Good night,
Thanks,
good morning,
everyone.
good afternoon.
Great weekend.
Yeah, great weekend for sure.